All right, so I'm going to go over a problem that's in the book over forces with an Atwood machine. So an Atwood machine would be basically kind of like looking at an elevator, where here you would have the elevator and somebody inside it. And then on the other side, where you don't see, is a counterweight of some kind. This isn't necessarily exactly the way that an elevator works, but you get the idea. And then, of course, in this case, we're not going to have a motor either, because this is a system in which is just draped over a pulley with two masses. Of course, they're offset. So the one on the right has a mass of 3.2 kilograms, and the one on the left, M1, has a mass of 2.2 kilograms. And so it's going to accelerate to the right, where the one on the right, M2, goes down, and M1 goes up. M2 and M1 both are 1.8 meters from the ground, from the bottom of them, and the center of the pulley is 4.8 meters from the ground. So here's the question in the book, essentially. I'm not reading it verbatim, but basically, given that this system is set into motion, it's going to accelerate, of course, in the direction that I had just said. It's going to accelerate in this direction. M1 is going to go up, and by the way, if this goes down 1.8 meters, then this one will go up 1.8 meters, and it's already some distance off the ground as is, being 1.8 meters, so it's going to go up an additional 1.8 meters by the time that it's done accelerating. Then at that point, it will continue to go up because of its momentum, because it's going to be carried, and it will eventually come to some peak height. So we essentially have three problems here. Problem number one is using the Atwood machine in order to figure out what the acceleration is in this direction, which is the same as this direction, by the way. Then once we figure out the acceleration, we're then going to figure out the final velocity of M1. What is the final velocity after having gone 1.8 meters up? And then lastly, part three of the problem would be to figure out how high it goes due to its momentum. All right, so let's kind of erase this stuff, and let's get to the meat and potatoes of the problem. First off, I've solved this problem before. I actually have another video on my YouTube channel, at least at this moment, where I treat up as being a positive direction and down to being a negative direction for both masses. So for M1, up is positive and down is negative, and for M2, the same is true as well. In this case, I'm going to treat this differently, and I've learned that it solves the problem in a much simpler fashion. Instead, I'm going to say that the direction along this path is a positive direction. So for M1, up will be positive, and for M2, down will be positive. So along that path will be a positive direction. What that does is it allows the acceleration to be positive for both masses. And it does simplify things. What I'm going to do is to start off to find the acceleration, I'm going to basically have two unknowns. I'm going to have the force of tension will be an unknown, and the acceleration will be an unknown. If I have two unknowns, I need two equations. It's a good thing that I have two masses. I'm going to apply the second law to both of them. So the sum of all forces for the first object is equal to M1A, which is in turn equal to, as we said, so this is going to be, so we have the force of tension acting up, and we have the force of gravity acting down. In fact, I'm just going to say that's M1G. And I'm going to try and make them somewhat proportional. So you should recognize the force of tension is going to be larger. So I have the force of tension minus M1G, because we said that this was a positive direction, this is a negative direction. I'm going to leave some space and do the second one. So the sum of all forces for object 2 is equal to M2G, which is in turn equal to, well, let's take a look at it. So we said that this is the positive direction. So we have the force of gravity acting down. Let me actually take this away. So I'm going to say this is M2G, and then acting up, and it's going to be a smaller force, force of tension. These two forces are the same force. That's an arrow, sorry. So in this case, we have M 2g is a positive value minus the force of tension. And these are the same force of tension between both equations. I want to solve for the acceleration. And I made a mistake. M2a. Sorry about that. M2a. Well, that's embarrassing. Not too much. So the sum of all forces for object 2 is equal to M2a, which is in turn equal to the resolved forces that I'm looking at. So in this case, the force of gravity, which is positive for M2, and then minus the force of tension. All right, glad I caught that now. That would be terrible. Since I have two unknowns, I really want to solve for the acceleration. So what I'm going to do is I'm going to solve both equations for the force of tension. Then I'm going to set them equal to each other. Then at that point, I'll be able to solve for the acceleration. So to solve for the force of tension, let's see. For the first one, let's go back up to that. The force of tension will be equal to M1A plus M1G. And then for the bottom equation here, we've got that the force of tension is equal to M2G minus M2A. So now I just set them equal to each other. M1A plus M1G equals M2G minus M2A. There we go. And since I've got the bulk of that done, I'm just going to go ahead and kind of get some of this stuff out of my way. We can make it a little bit smaller so that I can not get rid of it, but get out of the way. Now, that gives me some room. I want to get the G's to one side and the A's to the other, so let's go ahead and do that. So I'm going to add each side by M2A and subtract each side by M1G. So M1A plus M2A equals M2G minus M1G. So I did that kind of all in one step. If you need to pause and look what I did, go ahead. I'm going to now factor out the A's and the G's. So A times M1 plus M2 equals G times M2 minus M1. And now I simply divide each side by M1 plus M2. And that'll give me the acceleration. All right, there we go. There's the acceleration of the system. All right, so as I was saying, once we have the acceleration, we then have some kinematics problems. So let's erase some of the stuff so that way it's not so sloppy. There we go. All right. And I'm going to also kind of clean this up as well. Give myself some additional room. All right, so there's my acceleration. And I think I'm going to go over this conceptually, mostly. I'm not going to actually put numbers in. But here's the idea. Again, this is going to go upwards, 1.8 meters, and it's going to accelerate at this rate here. And it's going to come to some final velocity. Whatever that final velocity is, it will become the initial velocity of another kinematic problem. So let's look at that. We would take v squared equals v naught squared plus 2a delta y, where the initial velocity in this case is 0. That'll go away. The delta y will be 1.8 meters. The acceleration is going to have this value here. And in the see, we already have masses of 3.2 and 2.2 kilograms for M2 and M1 respectively. So we can go ahead and figure out what the value of A is, but I'm not going to really run through the numbers. But we can find the value. So B is going to equal square root of 2a delta y, where again, a is going to be the value of acceleration we find with those numbers. And the delta y is 1.8. So we find the final velocity. Once you have the final velocity, you then run it back through the same equation. But this time, we want to find what the change in height is. Now we're solving for the change in height, given that its initial velocity comes from here. So whatever the final velocity is here becomes your initial velocity here. Your final velocity is going to be equal to 0, because we're looking for how high its peak height is. So the final velocity will be 0 for the last part of this problem. And we're going to actually solve for the peak height. The acceleration is 9.8. It's a negative 9.8 meters per second squared because it's accelerating due to gravity. Do not mix up the acceleration that is happening here, because for this problem, we were looking at the acceleration that was occurring on its way up due to the pull of the Atwood machine. Here, this acceleration, it's accelerating down. It's moving up, but it's accelerating down because it's slowing down due to the acceleration of gravity. These are two different events. We really have, we have two different events happening. Three different parts of the problem with two events. Event 1 is the system accelerating, where m1 goes up. And then event 2 is, once it's done accelerating due to the Atwood machine, it will now start to accelerate due to gravity. We want to find the peak height. So we solve for the delta y. Don't forget to add in the starting height, the 1.8 times 2, right? And so station area 3.6. Okay. All right. So I think that's what I wanted to go over. And you can email me. I'll let you know if you have any questions about that. But I'd rather not plug in numbers just in case I'll use it for homework. All right. That's it. Take it easy.